Okay, there we go. Well, welcome to our latest session of the Healthy Planet Action Coalition Members Forum. And today we will be hosting two special guests. These two individuals have been working and publishing together in recent times. That is Tom Harris and Jan Umsonst. Now, Tom is going to kick things off by discussing climate change acceleration, looking in particular at the rate of, or the role of El Niños as ratchet moments creating jumps in global warming. Tom has a PhD in machine learning for signal processing, back before it was called AI. And he spent his early career as a university lecturer in engineering and researching neural computing applications, which evolved into a medical device company. Now he is working on climate science on his Substack, Climate Uncovered, which is a really good Substack that, in fact, was the way in which we at HPAC became aware of Tom's good work on that. Now, after Tom does a part one, then Jan Umsonst will dive deeper in some of the main signals inside the system that indicate we are in unquantifiable worst case scenario territory. And Jan is an independent researcher who works to understand Earth system changes and hunts for important changes in the Earth system. And he's been finding a lot of them recently, I would say. So with that introduction, let me turn over to Tom, and you could start sharing your slides and give us our introductory remarks. Tom?
So yeah, first of all, thanks for letting us use your platform and share the work that mainly Jan has been in doing. It has to be said. We've done three articles together now that have dived into the complexities of ocean heating in particular and cascading effects. So this is quite a good way of sort of bringing everything together. I'm just going to sort of set the scene and cover a few basics. I think everybody here will already know a lot of what I'm going to cover. So I'll try not to take up too much time and then hand over to Jan to really sort of dive into the detail. So yeah, we're going to talk about accelerating climate change. I'll just give you the very latest on Earth's energy imbalance, some stuff on acceleration. Then a dive into the El Nino, and we've got some up-to-date ideas of what that will do in terms of this ratchet phenomenon that seems to be appearing, certainly over the last three ENSO cycles at least. What does that mean for 1.5 and 2 degrees C in terms of thresholds? And then just a starter on where the energy goes and what happens within the oceans. And then, as I say, yeah, we'll take it from there. So we're all familiar with the Earth's energy imbalance. It is starting to get a lot more sort of credibility and a lot more discussed in recent months. The World Meteorological Office included it for the first time in their annual report this year. There was quite a good piece in The Economist this week that started to sort of explain it in more detail. And I think part of the reason for that is that now the CERES data is more than 25 years old. It's got that sort of credibility and that long reliable data signal. That means that it can be really sort of looked at and patterns can be extracted from it. So we're all familiar with this. The energy imbalance is the difference between the energy absorbed or coming in from the sun minus the energy that's reflected back into space by the albedo and also the long wave infrared, which is emitted from the surface. If the EEI is positive, the planet is warming up. It's as simple as that. it's an energy equation. If the EEI is zero, then the planet is stable, and if the EEI is negative, then the planet's cooling. And it really is, as I say, as simple as that. Looking at the data, and this is the very latest data. I updated the slides because a new month came out just yesterday morning. And if you plot that over the CERES era, so for the last 25 years, it was around 0.35 watts per meter squared. Now with the May data, 36-month average, it's 1.45. So it's more than 4 times higher than it was 25 years ago. And that's really significant. Obviously, the Earth has an awful lot of square meters, so that turns out to be a huge amount of energy, around the equivalent of 12 Hiroshima bomb blasts every second, and that's continuous. And I just put in this little link to this paper. The climate science community is recognizing the importance of this, and this paper is saying that the Earth's energy imbalance has more than doubled in that 25 years. And this really hints at some of the conservative nature of mainstream science, because they're taking an average of the first 10 years and an average of the last 10 years and smoothing everything out and saying actually that gap has doubled. But I think you and I would look at that and see that's a pretty straight linear curve, and it's quadrupled. So the situation is worse than the public is being told. Now, one of the interesting things you can do with that is integrate it, and I quite like to do that because it provides a really solid example of how this is accelerating, and that's a classic exponential curve. The accumulation just from 2000 onwards is 355 zettajoules. Zettajoules is a very big number, 10 to the 21 joules, and yeah, we can really see the acceleration in there. And that's why when you look at all of the other measures, so your surface air temperature, your sea surface temperature, your ocean heat content, absolutely everything is showing this acceleration signal. And the reason for that is very, very simple. The Earth is accelerating the amount that it's accumulating all of the time. There's a hand up. Is that for a quick question or?
Yes, I mean, have you actually fit that to an exponential?
I haven't, no. It's something I could do.
Yeah, no, it's
Easy
just that
enough
I've
to
heard
get
people
the-
say I've heard people say it's accelerating and it's an exponential as if those were identical, but I never see them a fit. But that's fine. I get the idea.
Yeah, it's yeah, you know what I mean. Okay, now diving a little deeper, you can break down the CERES data because it provides you with the short wave, it provides you with the long wave, but it also provides cloud cover information. And this is really interesting when it comes to looking at the albedo loss on the shortwave side against the long wave and the greenhouse gas side. And at first glance, this might suggest that actually it's albedo that's doing all of the work. But I think it's a little bit more complicated than that. I think in a normal stable system, if the cloud cover reduced or there was more shortwave entering into the climate system, the Earth's surface warms up, and we know it's been doing that. But that would mean that the long wave energy was able to escape. So the reason why the EEI is so high is that long wave clear in particular should be a very negative number, but it's being trapped by all the greenhouse gases, and that's what's causing that effect. The interesting thing about the cloudy side, where that is actually radiating more heat than it used to, is simply because clouds are warming up. So even though there's less of them, we're getting more. So the clouds are actually moving higher in altitude and actually warming at the same time. And because there's then less greenhouse gas to get through, we're seeing an actual sort of increase in the amount of long wave that's getting out. But obviously the shortwave stuff, very, very high amounts, significant loss of albedo, and a lot of that, particularly when it comes to the cloud cover, is being lost over the oceans, and that's one of the reasons why the oceans are warming up so rapidly, so fast. I'm sure everybody knows this in terms of where the energy is actually going. The main thing to take from this is that 89% is going into the oceans, but critically, over half of all of the energy imbalance is ending up in the surface of the oceans. And that's really important for what the rest of the conversation is about. So the ocean is heating up, and in terms of the amount of energy last year, it was 23 zetajoules of energy was absorbed by the top 700 meters of the ocean. Absolutely enormous amounts of energy, and it's no surprise that some of it's being belched back in the upcoming El Nino and all of the heat waves effects and so on that the yarn will cover. So this El Nino ratchet effect, we've got a super El Nino brewing. So the events are going to be really strong globally. We're looking at all the sort of floods and droughts and extreme temperatures and all the rest of it. But the El Ninos actually also provide the jumps in global average surface temperature. So it's not that the El Ninos are warming the Earth. It's that they provide those sort of step changes within the gradual acceleration. So it used to be that you had an El Nino event, the Earth would warm up ever so slightly. You might get half a degree or maybe even more than that in the following year. But then when you got the La Nina or a neutral phase, you got a cooling cycle that balanced everything out. That's no longer the case. And if you look at the examples, 2016 was a lot warmer, as you'd expect, because that was a very strong El Nino. But the temperature in 17 through to 22 didn't drop. Exactly the same thing happened in 23. So 23 was a strong El Nino, only just made it over the strong boundary. But that made 24 the hottest year on record at plus 1.6 above pre-industrial. And it hasn't dropped significantly since then. It's still half a degree warmer than the average was before the 23 El Nino. What we're likely to see in terms of the next one is something even worse. This is the chart of the predictions for where the current El Nino is likely to go. And just for example, I've put on the 23 strong peak and the 2015 very strong peak. And you can see that the models are predicting later in the year that this is going to be really something quite wild. It's just bonkers what's being projected. And if you look at what the El Ninos have actually created in the past, the 23 event was only just strong, but it did enable the Earth to warm past that lower Paris target for the first time, and that was a significant jump from the previous. The 2015 was very strong, and that tipped the Antarctic sea ice cycle into a new regime, and that's not recovered since. And if you look back even further, in the 1940s, a very strong El Nino event then is believed to be really quite a strong part of the reason why Thwaites, the Doomsday Glacier, started losing its pinning points on the ocean floor, and that the ice shelf started to break away. So, as I say, the forecast for next year are absolutely bonkers. Just in terms of what that means, just lifted some quotes from Mark Roberts' excellent Substack, his For Hunger. This is going to be really damaging from a food security, from a cost of living, but also from a severe famine risk in the global south. And what that chart is showing is the next 18 months of harvests and where the peak of the El Nino is going to sit, and it covers virtually the entire globe, is going to be struggling. Europe isn't actually covered on that, but Europe's already in trouble because we've got this enormous drought that's going on. We here, I mean, I'm on the borders of England and Wales, which isn't the driest part of the world. We haven't had any rain for 6 weeks, and that's just very unusual for the UK. So lots of bad things are going to happen. We'll leave it at that. Now, just in terms of temperature peaks, what can we expect this year? So that top graph there is is a correlation between the strength of the El Nino on the x-axis, measured at the Nino 3.4 point, and the temperature peak for the peak month of the following year, above the average either side. And you can see there's a reasonably strong relationship between the strength of the El Nino and the peak month that gets delivered. So just plotting that down onto the table on the right-hand side. Sorry, Bruce. There we go. If this is a 4 or even 4.5 degree, which some of the models are predicting, we can expect to see the first month over 2 degrees C in average surface air temperature sometime next year. Whatever happens, 26 is going to be an interesting year to follow. Jim Hansen is predicting that the 24 record of 1.6 degrees is going to be beaten. That may be quite a tall order, but it's a brave man that argues against what Jim Hansen is predicting. Whatever happens, 2027 will break 24's record and whatever 26 ends up being. And it's likely to be in that sort of 1.6 to 1.8, possibly even higher for the average temperature for next year. And because of this ratchet effect and the amount of energy being accumulated, the average after that, 28 to 30, is very unlikely to be below 1.6 degrees C. So that means, folks, that 2025 was the last year ever with an average temperature below the lower Paris target of 1.5. And that's quite a stark position to be in. Really, really quickly, does this mean we crossed 1.5? Yes. You could argue that the last 20 years were less than that, but actually, if you look at where the center of a 20-year period is going to be, it's going to be 25, 26, and 2 degrees C is going to be the late 2030s, possibly even as early as 2030, 36. And then this next little bit, just for some humor, is this sort of insistence that the IPCC has on using the last 20 years, even on a system that's accelerating. And the analogy is that if you got someone to have a cold bath and then they ask for it to be warmed up, you light a fire underneath it and it gradually warms up. It gets to the point that they want it to be. So 4 degrees C in this case, but as far as I'm concerned, it's the 1.5 threshold. The man complains and says, "No, okay, that's warm enough." "Oh no," says the IPCC, "we want it to be nice and nice and an average over a long period of time. So we'll leave the fire on." And unfortunately, the guy boils to death. So now, finally, getting into this sort of ocean stratification and the effects, all of this accumulating energy is going into the oceans, or 90% of it, and that's leading to a huge amount of stratification. So the top chart is a pictogram, if you like, of what would normally happen. You have a lot of movement and mixing within the ocean structure, and that means that the heat is being moved down into the deep water. It's not being sort of capped at the top. It means that nutrients can flow. It means that the carbon cycle can operate, and all sorts of good things happen. On the right-hand side, where we've got this accelerated warming in the top layers, it's producing this sort of barrier, which is stopping the mixing. It's trapping the heat in the surface. That means there's more heat that's available to get into the atmosphere and cause all the chaos. And it's also hampering carbon cycle and everything else. So the bottom two graphs, the one on the left is the stratification over the last, I can't quite see it, I think it's the last 40 years. And you can see that's gradually increasing. The one on the right is ocean heat content at the 3 different depths. And it won't come as any surprise that the blue line is the surface layer, and that's the one that's accelerating the fastest. And that's why we're getting these extreme waves, narrowing storm tracks, lower cloud cover over the oceans, which is driving the drop in albedo, accelerating the warming even further, extreme storms. Valencia is a good example of how a superheated Mediterranean Sea dumped so much water into the atmosphere through evaporation that over 200 people died in the subsequent floods, wind lowering, and a range of other biological and carbon sequestration issues. So I'm going to leave it there and hand over. So thank you again for inviting us. A quick shameless plug for our Substack. It's free. We invite you to come along and see what we've been writing about and so on. So I'll leave it at that and let Jan continue,
Thank
unless there are
you.
any questions for me at this stage.
Yeah, let's see if there are
I
any.
have a question. I have a question, which is
Ah,
this is Greg Slater, if you don't mind. The question is
sure.
you identified the ratchet mechanism. Do I take it that the stratification is the driver for the ratchet? The increasing stratification, what enables the ratchet, or else what is it?
Hmm.
Um, I think it's a general sort of function of the acceleration of the whole energy imbalance.
Hmm.
I think the stratification is certainly allowing more of the heat to be, if you like, stored locally and charging up a battery that's able to release it through these marine heat waves and El Nino events. I think the El Nino is coming out as the sort of defined ratchet because it's the largest release of energy from the ocean into the atmosphere that we have. I don't know, yeah, Jan, would you agree with that?
Yeah, absolutely. I mean, what ocean stratification does is I made it in my sheet I sent to everybody. We have now more and more ocean regions where heat is increasingly stored in the upper 200, 300, or 400 meters, depending on the ocean basin and region. And these regions become more efficient heat depots where the atmosphere can tap into. Take the North Pacific, it accumulates more and more heat in the upper 300 layers. It does so in the summer. You have massive heat waves, reducing cloud cover, more sunlight entering the upper ocean, heating them up. And then you have winter, and winter have the winter storms, and they release this heat depot. So it recharges during summer and discharges during winter. And yeah, so we have more and more of these heat depots, which can be more efficiently tapped by the atmosphere during winter or during El Niños or during tropical cyclone seasons, which contribute now increasingly to the acceleration of warming. And that's maybe
Okay.
one of the main issues we have now.
Yeah. Well, thank you. Thank you, Jan. Why don't we take this opportunity to turn over to you for your remarks? And
Um,
as you're,
I was a little unsure about what I want to do my presentation, and then I thought, okay, I take temperature jumps and more on the details, what we observe in the principal change of temperature jumps, and what are the sequence inside the systems, what happens during these temperature jumps. And this is actually quite interesting and quite fundamental to understand the future warming rate of Earth. Because temperature jumps define the acceleration of warming. It's the frequency of jumps and the intensity or size of the jumps. And most of the warming from these jumps happens via latent heat release from the oceans. But also we have other feedbacks also at play, like sea ice losses, heat waves, or the continents, expansion of subtropical dry zones, declines in relative humidity, declines in snow cover, and these kind of things that can also contribute to these temperature jumps. And so I went a little bit deeper inside that to explain what we observe in terms of temperature jumps and how they've changed on a fundamental principle level. So let's see if I can do the share thing. I go to my slide. Okay. Am I gone? Chuck? Okay, you can see it?
yes, we can see it.
Okay.
Yes. Very.
Wait, I have one thing I have to do. Sure. Okay, now we have it. Emerging tail risk in the Earth system with example of temperature jumps. What is interesting with the IPCC in its statutes, it's only allowed to include scientific discussions that reach consensus status. This means that discussions on tail risks and overlooked feedbacks, they are especially the discussions that need the longest time periods to reach consensus status. This means the IPCC, by its status, the tail risk was excluded. Though we have a risk assessment on climate change, which excludes the tail risks. And this is very fascinating for me. It's upside down risk assessment, actually. We have to include tail risks. And this means you do not have consensus status on tail risks, but you have to discuss them also openly in IPCC reports. But this they do not do. And these temperature jumps increasing in size are for sure tail risk. So we go on. We start here. This, all these temperature graphs. I like this one the most because it includes all the different temperature data sets. And most, you can see my mouse pointer, I think. Here, 1877, 1878, we had an El Nino. It's coupled with a positive Indian Ocean dipole and a North Atlantic warming. And it produced a jump by some 0.5, 0.4 degrees in an unforced climate system. So this means if the system is able to produce a jump in an unforced climate system, the question is, how large can a jump become in a highly forced system? And we had these jumps again in 2014 to 2016 and in 2023 and 2024. We had two of these jumps in the size of 0.4 degrees. And I measure these jumps from the point where they start. This means you have a 2014 or 2013, a lower average temperature than from the mean. And from this point, if you go this temperature jump, you have some 0.4 degrees. The same with the last jump, also some of 0.4, even a little bit more, depending on the data set. So from the temperature level, these jumps start in a given year. They add at least 0.4 at the moment. And maybe we can get jump 0.5, 0.6, we don't know. But it would be likely that we get a greater jump because the system accumulates ever faster energy. Also, greenhouse gas levels rise ever faster. So it would be just, it seems likely that the system is able to produce a larger jump than we had before. This is the tail risk we have. We can get a jump by 0.5, 0.6 degrees, let's say 2031, 2032, which would bring us close to 2 degrees or even above it in a matter of 2 or 3 years. So this is one of the tail risks. And the other tail risk is you can get in a higher frequency these jumps because the system accumulates faster energy. And it seems that the oceans are the main driver of these jumps. It's greenhouse gases levels increasing in the atmosphere. The oceans accumulate ever faster energy. This enables them to release more of this energy during these jumps. So it's a recharge, discharge oscillator Earth in a sense. Yeah. And if I'm a bit fast, I'm sorry, I'm a bit nervous. So let's see next one. This is just here temperature, sea surface temperatures, because they will play a central role in the whole thing. These jumps in air temperatures, they are accompanied or tracked by jumps in sea surface temperatures. And during the jump in 2023, 2024, actually the sea surface temperature increase were leading the temperature increase in surface air temperatures. But this will come later. Just that sea surface temperatures are very important for these jumps. They have to increase likewise to enable these jumps to really develop a large temperature increase signal. So here the next one. This is interesting. It's just the upper one shows El Niños, La Niñas. You see in the 80s a very large El Niño from the surface temperature in the tropical Pacific in the Enzo region. And then you have in the 1997, 1998, this extreme El Nino. And we have had again one in 2015, 2016. And now look at the last El Nino, big one, 2023, 2024, because in terms of heat expression at the surface, it had not been too strong. And especially in terms of latent heat release, the last El Nino had not been a strong one. But this also we'll see later. Just here is important. If you look at the lower graph, you see the temperature contribution of the single jumps to average temperatures. And you see here the El Nino 1990-88, which had been quite strong, just produced a small temperature increase. The 1998, this one was quite large. And the 16 one, 2016, had been the largest in this graph. But the one in 2023, 2024 had at least been similar than 2016, but it had been a weak El Nino in terms of latent heat release. And we will see in this presentation what caused this temperature jump, what subsystems in the Earth system contributed to the temperature jump we had in 2023, 2024. And this enabled us a little bit better to evaluate in how far we can expect larger jumps if you understand how these jumps operate. And now we have actually all the studies we need to assess what happened in 2023, 2024. There were questions because I heard, I don't know, later before the sound. If you have questions, just ask. This is the temperature D shows 1998, where you have temperature anomalies during the strong El Niños. And the other graph shows 2014, 15, and 16. It's from a study which analyzed the temperature expression of the El Niño and compared it to these past El Niños. And you see that regions beside the tropical Pacific contributed much more to this warming jump than you had it in 1998. What you see is one side are ocean temperatures. You see in 2014 here, for instance, west coast of America. This one had been important. In 15, it even grew in size. This ocean area had been important. Overall, you see that the whole oceans had been warmer in 2014, 15, and 16, anomalous warm than in 1998. So the ocean contribution of the extra El Nino regions increased during this El Nino compared to the 1998 one. And also you have a temperature signal in the northern high latitudes where you also have a large temperature increase during 2015, 2016. This component is also important for these temperature jumps as El Niños tend to produce heat waves in the northern latitudes, especially in the northern hemisphere during winter, but also in the southern hemisphere. And this we had with the last El Nino during 2023, 2024. We had very extreme heat wave in the Antarctic during some months, which had a large influence on these monthly temperature extremes we had. For example, September 2023, when we had this first massive peak in monthly temperatures, we had also massive heat wave over Antarctica. So both polar regions are now contributing to these temperature jumps because the Antarctic was not too much part of it before because it was not too warming too fast. But now we have sea ice losses, a southern ocean is warming, and also these massive heat waves now over Antarctica. And these heat waves during winter then can have temperature anomalies of 30 to 40 degrees above normal. So you have not a small area, but you have an area with very high temperature anomalies which are unbeaten on the planet. So this means you have instead of minus 50 degrees, you have minus 10 degrees over areas over Antarctica, but also minus 20, minus 30. So these peaks, minus 40, are local max values. But in general, you have heat waves with the highest anomaly values on the planet over Antarctica. So these heat waves really contribute to monthly temperature peaks during these temperature jumps. And see now next, this one here. Now I'm with, okay, okay. This is just the first one. It's just what happens during the last temperature jump. Because we had a record rise of near the zero 0.4 degrees during that time. But most importantly, the study states that most of this warming happened because of the oceans. They write 92%, but I think it's too high. But it was a
Jan,
very large contribution from the oceans. Yeah.
I'm sorry. Let me. I'm getting an echo. 1 second. I'll
Mhm.
clear that.
Go ahead, Jan.
Okay. Interesting was, for example, in this temperature jump, we had a tropical wide ocean warming during 2023, 2024, during some 4 months. The tropical oceans went into a hot state with different, a little bit changing warming pattern, but it was actually an exceptional temperature signal over large parts of the oceans, especially the tropical oceans, but also large parts of the subtropical oceans, also North Atlantic or North Pacific. And so the whole ocean went into a hot state during that time, in terms of what we had observed in the past. Later, we will see and to look more closely in these signals, but it was really impressive what the oceans did during this jump. And genau. So let's see next one. This one is
Jan,
here. Yeah. Go ahead.
okay, sorry. Can you hear me now?
Yeah.
I think so. Good. Okay. So I just wanted to backtrack a little bit because you're covering a lot and it'd be nice to. So what in your estimation would be the reason that for the extreme polar heat, particularly in the Antarctic, as you say, because what we seem to have the ratcheting, but it also seems to be uneven geographically. And we've known for, polar amplification for a long time.
Mhm.
But perhaps you have some insight into
Mhm.
that
I mean,
in particular.
The Antarctic is interesting. Heat wave over the Antarctic are mostly a result of moist and warm air being really pushed over the Antarctic. That's one mechanism. And these large transports of warm and moist air deep into the Antarctic produce during winter these massive heat waves. They don't last too long, but they have really an effect of monthly mean temperature values, global ones. And this is one of the main reasons for these heat waves. And what you have moisture building up near the surface in the warm month. This means you have what we understand now, the temperature increase in the Arctic. And in the past, we thought colder regions warm faster than warmer regions. And now we realize that the warmer regions in the Antarctic, like the West Antarctic during summer, warms faster than the cold regions. And the reason is if you have warmer temperatures above minus 20 degrees, you get water vapor. And the water vapor reduces the outgoing long wave radiation, though the temperatures have to heat up more to give up more long wave radiation to space to reach equilibrium. So this study was published 2026, I think. So we just discovered that the Planck feedback over Antarctica is reversed. This means warm regions warm faster than cold regions. This is also another reason why the Antarctic is now warming more, because mean temperatures rise, especially during summer and West Antarctica, but also during these massive heat waves, you go below these minus 20, and this water vapor feedback also kicks in. And you have now these sea ice losses around Antarctica and the reversal of ocean heat in the Southern Ocean, where more of the subsurface heat comes now to the surface as the surface became saltier from 2015 onward. This means you have now a warming Southern Ocean as well, and sea ice losses, which disturb circulation around Antarctica. You have waviness jet streams or more waves in the jet stream, which allow also that more moist and warm air, air is more often entering Antarctica and producing these heat waves. They can happen also
Yeah.
during summer, but they increase
Thank
now
you.
during winter. Okay,
Yeah.
sorry.
Thank you. Yeah. There's a lot there. I think hopefully there's some, modeling of all this because, it's very hard to track all these different effects in a verbal, presentation. But thank you.
Oh God, you asked me. I didn't have prepared and graphs and stuff like this.
Yeah. No, I get it.
Just tell it.
Yeah.
This is what you see here is a 2023 surface temperature anomaly rank in the left one. And you see that most of the oceans reached very high values or exceptional high values never reached before. And so we had a very large intensification of sea surface temperatures driven by marine heat waves in 2023. And it was exceptional, this signal, how fast wide parts of the oceans heated up simultaneously. And most of this signal happened from the second half onward. The last 6 months, this signal actually was produced over most of the oceans. And on the right side, you see on 1997 sea surface temperatures during the El Nino, 1915, where sea surface temperatures increased, and during 2023, where sea surface temperatures increased. And you see that the synchronization of sea surface temperatures during El Nino events is increasing very fast from a spectral perspective. The area is really, you compared 1997 to 2023, the lower one. It's like day and night in a way. So the ocean surface becomes more susceptible, more vulnerable towards temperature jumps. And this is also related also to stratification, but also to atmospheric changes like more blocking patterns or moisture transport to the poles. So you have now actually several mechanisms that drive marine heat wave in the oceans, and also low cloud cover because of abnormal high pressure systems. You have low wind speeds that reduce upper mixed layer, which can heat up faster. So you have now several processes which can all in itself produce these heat waves. And all heat waves are different but similar in the oceans. But what we see is that the surface oceans become more susceptible towards fast heating periods ending in these marine heat waves. And we will go see later how the whole signal developed, because only if you can see it for yourself, you realize what is happening on the surface oceans. And this is maybe one of our main problems, how fast marine heat waves intensify. And just the signal on the right is impressive in my point of view. Let's see, next one.
Jan, could you wind up pretty soon, because we want to have some time for questions and
So
discussion?
yeah, I thought actually that it gets to, but we watch now just the marine heat waves, and then we will stop, though you can see it for yourself. Because actually, my problem is if you want to explain something on Earth system level, you need time, you need hours actually. Otherwise, you cannot make all the connections. But this is the reason I like more to make these presentations in the form of PDFs and send it to everybody so they can work with it. But just this one we show together. This one is the signal. What you see here is actually the signal how marine heat waves developed in 2023. Just August, September, October, December, December. Now it starts. Look how it spreads. And we do one more. And one more. Very cold, a lot of air is cold, and now it goes. Bum, bum, bum. This is mostly wind speeds, what you have there, and blocking patterns, which drive these increases and related to cloud cover decreases during that time. So actually, it's the synchronization between the upper ocean and atmosphere that produces this jump. It's not just stochastic forcing. This is a system that goes into synchronization mode over the most of the surface, also including continents, moisture gradients, and stuff like that. But these oscillation events we can expect also to strengthen in a warmer climate because you get higher stratification levels, warmer upper or higher ocean heat content, stuff like that. And yeah, this is a signal of what to come. We missed totally how fast sea surface temperatures can increase. And now we look actually at the whole thing. This is development. Oh, what is this? Unexpected error. What is this? Okay, let me see. What is your problem? I don't know. But okay, anyway, never used that, just wanted to play. I did. No, doesn't matter. What do you have? Wait. Oh, I have always this here. I loaded. No. Whoop. I load. Let's see. Yes, okay. This one last we go, because this I wanted actually that you see it for yourself. This is we are 2013. This on the left here in the Pacific, it's the first heat wave, the first block. It happened during winter because of reduced wintertime cooling. This is where weak surface winds during winter that produced this heat wave. And it was the first massive marine heat wave which lasted till 2016. So it's over 2 week steps, just 2 week steps without any selection, just actually every 10 days a step. And how it progressed. This is also very important in North Pacific. You see these massive heat waves, they start already 2014. It's not just IMO, shipping regulations, and termination shock. The whole thing started then already. It's very important to understand. Here you see North Pacific, how it explodes. Here the Arctic also, very strong heat waves. This was the first pulse, you can say, that started in 2014, 2015, 2016. So the first pulse of marine heat wave, which had been repeated in 2023, 2024. And it was much stronger then than during that time. And now we have 2015, just progresses. Just also important, look at the southern oceans. These heat waves, they appear in both hemispheres and way before IMO regulations, and also in the southern hemisphere where you have no aerosol effects. Actually, there's a discussion that in the southern hemisphere they intensify also. This is now also important. This is during summer. During summer, you have an amplification of the seasonal cycle. This means the summer heat wave in the northern hemisphere, they're more intense than during winter in the southern hemisphere, and during winter then, or during winter in the southern hemisphere, it swaps the signal. Yeah? And just see the areas that how they expand also. This is now during the El Nino, where we had this jump in sea surface temperatures also to a minor extent. Also Indian Ocean, the sea mode going hot for a time, but so the whole thing morphs. But you see also large parts where you have still a colder temperature than normal. These parts will more and more vanish in the later years. And also what is very important, in 2016, the definition of marine heat waves had been first time defined. So the first time science defined marine heat waves as a phenomenon had been in 2016, 10 years ago. Before, we had no idea that marine heat waves in the oceans are important or can happen to such a degree. The whole thing is quite new, 10 years. We make now research on marine heat waves, or at least many, many papers since then. And here you see also southern hemisphere, these heat waves that pop sometimes up. So it's really a signal of both hemispheres affecting all the ocean areas now, depending on season and year. So it's a really global system of ocean surfaces heating up from time to time with massive signals sometimes. So The whole thing is just 6 minutes long, but this I wanted to show you because you have to see it, otherwise you don't understand what we have here.
Mhm.
Now it's
Okay.
2017.
Yeah.
Huh?
Can
I
you
mean,
wind up?
no, this I want to show. If you have no time, you can go. I mean, but the problem is, I'm very, this one is important. If you have no time to watch that, don't cool the climate. That's my opinion. If you have no 3 minutes to watch that one, no. No. It's really important. You have to understand what happens in the ocean. If you do not understand what happens in the oceans, no chance. We die out. That's my position. This one, yeah, it's really like this, Dennis. You have to see it. If you do not see it, if you do not see how it intensifies, how it spreads, and how strong the signal is, if you do not respect this signal and we continue to heat up the planet, the oceans will fuck us. That's certain. And it's not aerosols, it's feedbacks. And this you see also in Northern Pacific here. It's 219. This is before EMO. It's very important. All this termination shock nonsense, it happens way before these signals. So it's very important to separate it from aerosols. They play a role, they are important, but these heat waves are feedbacks. They also they lead to faster accumulation of heat in the oceans. And they discharge the heat during winter again. So the whole thing, also they shift ocean heat uptake to shallower levels, depths. They intensify stratification where they happen. They are a system changer. Marine heat waves are maybe the reason we die out because they change everything. And if this system further intensifies, we get massive problems because this system also intensifies all sorts of extremes. Name any extremes, they can intensify them. And it's a heat depot that builds up near the surface, which allows oceans to accumulate faster energy and discharge it to the atmosphere more efficiently. And
Okay.
yeah, that's important, this one. And now we have
I think
2021,
we get the
almost.
yeah. I
No, we
think
have some we have some minutes left because we have the last years, 2021 just. We go to 2025. It's just some more minutes.
It's probably also worth noting that there's some of these changes are rate dependent.
Yeah.
And the surface ocean is warming so quickly because partly because it's warming so quickly that it doesn't have time to sequester some of that heat down to the deeper mixed layers. So rate dependent tipping, rate dependent warming is a part of this as well, isn't it?
Yeah, full. And you have a higher wind variability. What we have now, very often you have these heat waves building up just because of weak winds. Weak winds are enough to let the surface ocean temperature explode. And we have now more of these blocking events, larger subtropical highs. We have sometimes sea surface gradients over the tropical oceans, which reduce surface winds over the whole tropical oceans. So this means the system is globalizing and it's intensifying fast. And we are just here, this one, Canada. This had been likely a vortex in the atmosphere collecting smoke, black carbon, which heated then this surface south of Greenland to astonishing values. And this had likely been smoke in a high pressure system, but I wait for a study on that one. It was just crazy and nuts, this one. Also, we have now diabatic heating up these heat waves. This we see in 2024, a heat wave that reached 8 degrees above normals in the middle of the oceans. 8 degrees warmer than normal in the middle of the oceans. That's insane. It's just insane. This year, the signal, here's tropical oceans now start to run hot here. This is the whole
Can you
Atlantic.
explain a little bit what the source is of the ocean heat waves? You say it's not aerosol, so it's not the irradiation coming in from outside. Is it sort of the disability to dissipate the heat to lower less? What's the cause? What's the energy trigger of ocean heat waves?
The problem is each heat wave is different but similar. This in the Atlantic, for example, had been analyzed. It's 3 heat waves. the northern tropical Atlantic, the equatorial Atlantic, and the southern tropical Atlantic. Here you had weak winds, low cloud cover, and declined upper mixed layer depth. Upper mixed layer gets thinner, it heats up faster, does not even need more sun radiation to reach the ocean. You have just smaller volume that heats up faster, and we have doubled the radius. The forcing from greenhouse gases is already close to double if you take CO2 equivalents. So all greenhouse gases increase together. So this means the forcing from the greenhouse gases is now able to heat up ocean areas very, very fast, just if you get weak winds, higher surface temperatures, then reduce cloud cover, increase stratification, though the heat cannot escape to greater depths. And here over the equatorial ocean, you had, I think, was weaker winds and also declining mixed layer depth. In the southern area, it was a subtropical high pressure system. Also, I think low cloud cover had not been main reason, but also mixed layer depth decreases and weak winds. You had there downwelling latent heat, which I heard for the first time. This means you get so weak winds that at the surface ocean, the air, the water vapor in the air condenses again to water and releases the heat of the condensation back to the ocean surface. Even this you get. It's a totally new mechanism via ocean surface can heat up. You just need very weak winds. And the
Thank you, Jan.
atmosphere,
I also have a question
give
to
it back.
Tom. Tom, you said that 89% of all the heat went into the oceans. That is a significantly higher proportion as a surface proportion of oceans of the Earth's surface. I always thought that hard surface can absorb more heat than water, but you may argue that the oceans, of course, can dissipate the heat further down, and therefore the accumulation could be. Is that the argument why it is 89% rather than the 72 or 73% of the surface proportion?
Yeah, that's right. The water has a much higher latent heat capacity, so it's able to absorb so much more. I think probably the land also radiates it away more efficiently than the surface of the ocean, so it builds up. There's also this mixing which allows it to store the water at depth, or store the warmth at depth. Or it or it used to be before the surface, that sort of pycnocline layer that traps the heat in the top layer. But that's that breakdown of where the heat accumulates across the land, the ice, and so on is very well documented and has been for a while. Yeah.
Thank you.
You see now signal also here in here this one. This heat wave was in local hotspot 8 degrees above normal. This is diabatic heat from the tropical cyclones and tropical monsoon rainfalls producing hot upper air that descends over the high pressure system over the North Pacific. This we get also. We trigger here a steam engine. Very problematic that we reach now this heat wave with such high intensities. Just now we have another one also in the North Pacific building up, but this time more through the east. So this whole heat wave signal is intensifying very fast. Now it slowed a little bit down end of 2024. But then regains strength again in 2025, and now in 2026 we have already again maximum values, and it's also heat content increase during the upper 100 meters. What happened, what enabled the signal in 2023, 2024 was prepared in 2022, 2023. So it's a ocean that is preconditioned in previous years by ocean heat uptake to produce these signals. And seems it's all inside now. It's studies being published more and more. We just understand the signal, and it's a really new signal in the system, and it should teach us respect. And if we make the mistake and think this is just aerosols and not feedback, we can end very fast in big problems because this won't slow down as it seems. And if
Mhm.
it doesn't slow down, we continue increasing greenhouse gases, we can get very fast into huge trouble. So, yeah. I just whoop. Okay. I had prepared more like what happened actually during this temperature jump, what drove these increases and which region, stuff like this. But this is the problem. It takes time. And to explain Earth system changes in the context, I would say you need days to
Mhm.
really go into it, what happens. And the problem is only if you understand the mechanics behind the changes, you can assess how the system will further evolve. And that's the main problem today because people have no time to dive into it. So I will continue to make my, not presentation, but where I list all these changes and bring them together. And people who want to work through it can do it and can learn how the whole thing operates. And yeah, so thank you for letting me acknowledging my presentation. But I thought actually it would be anyway too long, so I tried to make it very short. But it was, yeah.
Well, thank you so much, John, Jan, and Tom. You have brought onto the stage here a phenomenon that I think few of us were really aware of, and that is the enormous and very recent development of heat waves as a major forcing or a major feedback that we've got to understand. Yeah, fantastic. Well, let's
Marine heat waves.
Let's open up the floor for questions. And I see we have one hand up so far. Ron?
Yes, thank you very much. Oh,
Oh,
wait a
you
sec, 1 second.
you have an echo. You probably have two devices
Yeah.
up.
Okay, I do have two devices. Okay, now I should be okay.
Oh,
So am I okay? Yeah.
yes.
So thank you very much, Tom and Jan. I mean, it's really fascinating, stuff, and very, very alarming. Would it be so? Of course, as you know, we're quite, one might say, obsessed about trying to figure out a way to do something about this, and it's the action part. So, would if what you're saying to me seems to be that the accumulated heat in the ocean is coming back to bite us big time.
Mhm.
It's been accumulating for
Yep,
a
yep.
long time. For a long time, it was kind of storing the heat. Now the heat is coming out and causing all kinds of problems. So, I mean, well, obviously we would like any kind of way to cool quickly, near-term global cooling. We're not particularly, there's no, uh, we have no particular, attachment to aerosols or IMO regulations or any of these things. It's just, so what would you suggest to do about marine heat waves? I mean, if it seems like, as humans, of course, it's harder to deal with the ocean because we don't live in the ocean. But perhaps you have some suggestions as to other pathways to cool the planet quickly, including
Excellent.
the oceans.
Yeah.
I mean, what? I mean,
Pathway?
problem is, I mean, ready, Dennis?
Uh, Go ahead, Jan. Ron
Okay.
is
I
asking
mean,
about
the problem with
pathways
the
to
oceans,
solve the problem.
the problem with the oceans is, for example, these heat waves happen because of circulation changes. This means under high pressure is one of the signals and weak winds. So it's difficult to cool them down with aerosols because one thing is they dry out clouds in the lower boundary layer, and this drying out of clouds, this evaporation of clouds happen via cloud droplets. They are evaporated. With higher numbers of cloud droplets and smaller diameters, this drying out can happen faster. So you can even reduce clouds by aerosols over a marine heat wave in the troposphere. I think you have to go over the stratosphere. And anyway, we have to try to cool them down also in the troposphere, but maybe it doesn't work if they get too intense and circulation changes are too strong. But the main problem is what is till now not evaluated or tested with models is to what extent can you cool down oceans because via aerosols? Because the problem is we are, in my opinion, in the process to overheat the oceans. The moment we have really overheated them, stratified them strongly, and they have accumulated lots of heat over the first 500 meters, we are in big trouble. Because then you cannot cool down Earth with aerosols because we have too much heat in the oceans, and the oceans can only lose heat and cool if they release heat to the atmosphere. This means the stronger you try to cool oceans at the surface, the more heat they start to release. And they have heat for many, many years of keeping warming levels, or at least to resist a very large cooling. So if this is the case, and overheating of the oceans is maybe the main problem we have, this means if we start too late to cool the oceans, while we try to reduce greenhouse gas levels, because we have to bring ocean heat uptake down, it won't work at all, maybe. And this means we, at one point, I think we are now at the point where we will come into the situation where humanity will have to reduce greenhouse gases very, very fast to prevent oceans to take up more heat. And this means abrupt reductions of greenhouse gas levels, and for that you need 8 billion people working at our best. But it's not clear, maybe hopefully not. But if it's the case, the next 3, 4, 5 years, and we do not react with all we've got, we are finished. In my
This is
opinion.
a very stark warning. Yeah.
Jen,
Quick.
can I just respond? Sorry.
Very quick. Very quick.
Yeah. So if we need to cool, if we need that, I mean, getting the greenhouse gas out really quickly, I don't think any of us would object to that. Of course, if we could do that, that would be absolutely the thing to do. But in a situation where, because of social political issues, I mean, I think Tom has written about this very eloquently, you know, that it just takes a very long time to do that. Don't you have to deploy whatever kind of cooling methods you can to try and reverse that energy imbalance, at least temporarily, quickly? Okay.
Yeah.
So,
all at
Yeah,
once.
there are-
You have to
there are
cool as
also-
much as you can do, hope it works as much as you hope it does. But if we make a mistake and we would have to reduce greenhouse gases, and we did not tackle that problem as fast as we can do. 1 trillion drones in the atmosphere, you know, something like that. I don't know how many drones you need, but it would be a massive effort. But Tom, talk. So
Yeah, there are also some sort of political risks of going too soon with cooling as well, because if you, let's say that you decided to go ahead and do stratospheric aerosol injection sort of now, and either it didn't work, or there was a political backlash, or you didn't do enough of it, or there was some unexpected side effects that the modeling hadn't come up with, that could wipe out any hope of doing it again for decades, because it would be it's been tried, it didn't work, we need to find something else to do, or just sort of live with the consequences. So I'm cautious that there are geopolitical risks of going too soon, as well as physical risks of going too late.
Okay, thank you, Tom. Let's move on to Greg Slater.
Yeah, thank you. Well, both of you guys, thanks for your presentations, particularly Jan's. I mean, they're both good, but Jan's was something of a revelation to me. I just hadn't seen his position. I'd seen Jan's threads, and I have to admit, I counted him as a doom, just what they call a doomer, sort of, because I'm saying this just because this is where it came across to me, because his writings were very apocalyptic compared to what everyone else seems to be saying. Back off from the apocalyptic talk, because you're just, you know, that's not working. So but yours seem much more apocalyptic. But I'm now more inclined to give more credits to that. But just let me ask a couple questions. I mean, this came up between you and Ron, but you particularly cautioned against the potential effectiveness of low altitude things like marine column brightening in particular because of the effects you identified. If we did SAI, forget about the political apocalypse that Tom cautioned against, but if we just did it, I mean, what are the dangers of doing SAI from your perspective in analyzing the ocean situation, and as in the stratosphere? If you could just very briefly, again, I'm talking about the physics, not the sociology. Identify the risk there.
I think it's biology and winds. If we do psi and reduce incoming sunlight and reduce maybe gradients, because we cannot cool down the polar region as much as the tropics, it's all open. Though we can weaken surface winds, then you get heat wave expansion, because they just need weak winds, which is forcing. And the other thing is biology, you can really explode via weak winds, these toxic blooms of species. The weak winds, they can produce massive plumes. They just need very stable water column. So we can produce massive methane emissions. So the whole thing can go 100% wrong. And that's the main problem with psi. But anyway, we will have to try it. But when we try it, we have to be very fast in adapting our measures, and we have to really observe the whole system down the water column and really to check the changes. Though we are not surprised, and the moment we see, oh, the whole system is collapsing, we need to stop. But if our problem is too fast heating up oceans and we get too much heat in the oceans, in the upper oceans, because they're already stratifying, then we have only one thing we can do: reduce very fast greenhouse gas levels. And this is not clear. I follow the precautionary principle, and I think I have a lot of arguments to say it could be that we overheat the oceans. Now we have a super El Nino 2 years after the last temperature jump. That's insane. So just want to say, if this is the case and this comes out the next 3 or 4 years, because oceanographers are now fully on it, then we act with all we got, or we go extinct, because we increase the greenhouse gas levels way too fast. The oceans had no time to adapt, and what we trigger is the first time in Earth history, because the climate had been never warmed so fast, 4 to 10 times faster, maybe 100 times, but 4 to 10 times is a conservative ratio. 4 to 10 times faster on a bicycle, whoa. And that's the planet here. So that's just my position now.
Thank you, Jan. This is getting into some very interesting territory. I believe you're arguing that cloud brightening and lower troposphere aerosol loading could be ineffective in terms of reversing these marine heat waves, which are so dangerous. Could you go on to look at what might be the effects of using stratospheric aerosol injection at very high levels in the atmosphere, and how effective it may be in stabilizing and reducing global temperatures by reducing the release of heat or the buildup of heat in the oceans?
My
Could
opinion,
you
I think,
contrast the two? We got tropospheric aerosols, we've got stratospheric aerosols.
I think you have to use both. And the main thing maybe we will have to do is alter wind patterns. We have to play with gradients of the planet, because the planet plays with gradients to heat up. We can maybe play with gradients to cool it down. Stronger surface winds over the oceans, but it's also tricky. It's a trade-off. We have really with I think gradients will be important. I think big downsides, the whole stratospheric aerosol injection, you change heat gradients in the stratosphere, and all these gradients they steer circulation. So we don't know in how far we change stratospheric circulation and what this will have for effects for the troposphere. So it's a big unknown. And when we start, we have, I think, not really an idea of the side effects. We will have to learn while we do it. And we have to really observe the system very closely to understand what is happening so we can stop earlier than to produce the worst case or make it different. So, yeah.
Yeah, very, very good. Very, very good response. That's very, very concerning. Hans, you have another question. You're on mute, I believe.
Thank you,
Yeah.
Dennis.
Yeah.
Yeah, this is quite puzzling, of course. I also read a report by the WMO that the CO2 absorption capacity of the world's forest is already in decline since 2008. Because one of the reasons why fish is getting more expensive is that people can no longer fish that or catch their fish that they like to eat in front of their own coasts because they have moved on to the temperatures that the fish like. And so therefore, the Dutch, for example, have to now fish in front of the coast of Norway, and what you can catch in the North Sea, that's what the Spanish want to have because they miss it in their waters. Now, trees, of course, cannot do that. At least I have not seen a tree sort of pulling out the roots and say, this is getting too hot here, I'm moving to the better climes. So already we see the CO2 absorption capacity of the forests being reduced in 2008. And I want to ask, and it's good, Jan, that you're German because you maybe also, I forgot the name, but when I was 2 years ago at the Arctic Circle convention in Iceland, I was in a panel, and then afterward, I mentioned, of course, Paul Crutzen and the stratospheric aerosol injection, and I spoke with him for the first time about it, first in 2006 and then 2008. And then this German gentleman, whose name does not come out to my mind, he said, wie schön, dass Sie meinen Doktorvater erwähnen. So he said, I've done my PhD with Paul Crutzen, who of course you all know died a couple of years ago. And then he said to me something that I did not know, but was very pleased to hear. He said, did you know that Paul Crutzen in the later years of his life distanced himself of the idea of stratospheric aerosol injection because of the findings that what he had said earlier to me in 2006 and 8, that it would simply dissipate into space, appears not to be true, that some of it will actually come down, and then we may have a side effect as it rains, and we will exacerbate the CO2 absorption capacity of the other instrument that we have. And of course, we have to do reforestation, but I don't think we can do enough reforestation to simply compensate for reduced CO2 absorption of most trees not being in the wrong climate zone. So I was just wondering, you are all more knowledgeable about this than me. My side is more on the policy side, but I mean, where do we now stand? I understand what you say, that marine cloud brightening will have reduced effectiveness because the clouds that you can produce would evaporate quicker. That's on the cloud triggering path. There's also, of course, with marine cloud brightening to brighten existing dark clouds. And I think I'd like to hear whether you think that part of MCB is still worth doing. I understand that the other part may be less effective, but I'm a little bit scared about us now saying, well, we should do more SAI, because that may actually have as an undesired side effects that an already weakening CO2 absorption by the world's forest will get even more strongly weakened because of acid rains. Well, this is just what I hear say. I mean, I'm now amongst people that are very knowledgeable, so I'll be very glad to listen. And by the way, Robert, I would like you to speak out on this as well, because I know we're very much aligned on many things. So, Jan, where do you stand?
I think the kind of aerosols we need aerosols we can produce in high quantity. That's the main problem. So we need a good base substance. And I think bacteria is best, maybe because you can produce them in tanks, and we have all this bacteria and cell walls that lead to cloud formation also. I think in this area, there lies maybe the aerosols we need, because not too much side effects. We just have to culture them and to produce aerosols out of them. But I think we have to test. We have to test marine brightening, cloud brightening. We have to do it over a marine heat wave. How is the effect? Maybe it doesn't work, or it works a little bit. But the problem is they really dry, have a very dry air column, because you have no evaporation over marine heat wave, because very weak surface winds, which make this enable them to form, because heat loss of the oceans is reduced, at least during summer. So we have to test all the things, I think. And I think we are smart enough. But we need humanity working on it. And as a species, if we do it in the current political system, no chance, I think. We need
Just a note
humanity.
on the forest side and carbon sequestration. There was a very interesting climate chat with Dan Miller. It wasn't this last Sunday; it was a Sunday before, where they were looking at, in particular, the impacts of stratospheric aerosol injection on forests and photosynthesis. But that thing about the natural sinking declining is certainly a case. There was another study that came out that said that 2008 was the peak carbon absorption from the atmosphere as far as natural absorption goes. The tree side stuff is there's this kind of message out there that CO2 is plant food, and therefore the more of it you can pump into the atmosphere, the better the plants are going to be. And this is one of the common denier sort of tropes that they trip out. Number of arguments against that. One, obviously, is that all of these greenhouse gases are making storms, fires, droughts, and floods worse, which is actually getting rid of all of the benefit. But the other side that this sort of more recent research is showing is that although photosynthesis may be increasing, less of the photosynthesis is ending up as carbon storage in the wood. And it has to do with the water vapor availability and in particular the vapor pressure deficit, and that the cells need water and other nutrients in order to lay down the carbon. So they might be photosynthesizing like crazy, but it's not actually sequestering carbon at the rate that you'd expect for that level of photosynthesis. And that's one of the reasons why there's a natural decline. On the ocean side, the stratification isn't helping either, because it's messing with the whole sort of plankton food chain. It's stopping the movement of carbon around the different layers, and to a certain extent, our overfishing is having a massive effect as well, because a lot of carbon that would have been embodied in fish that might have been eaten by bigger fish that then died and then sank to the bottom, we're now scraping out of the sea. And decomposing it either by eating it or letting it rot or what have you. And that's releasing the carbon that would have been sequestered in the ocean back into the atmosphere as well.
Thank you, Tom. Robert.
Thank you, Tom and Jan. Really interesting presentations. Where I come from, just partly in response to Hans's suggestion, is that my sense is that the Earth system is just far more fragile and sensitive than immediately appears. And that means that in terms of a precautionary approach, we need to step back from the precipice of tipping points. And I think that the only way to do that at the moment is to deploy stratospheric aerosol injection as rapidly as possible. So the problem being that once tipping points accelerate, they're really impossible to slow down. And I'm particularly concerned about the collapse of marine clouds. The work that many NASA scientists and others have done on marine clouds indicates that they are the possibly the biggest tipping element, and yet they're not actually recognised as a tipping element. So I think that these issues of moving rapidly to deploy stratospheric aerosol injection, but the precursor for that is telling the story to the public in a way that is acceptable, and we still have not achieved that. And so just opening up the conversation about why that transition is urgent is something that I think that the sort of information you've been sharing today helps us to do.
I think we need to be a little bit careful about what are tipping elements and what are feedbacks. A tipping element is something that has at least two stable states with hysteresis between them. I think the marine cloud situation is more of a feedback, in that there's no point that you can go to that if you reduce the level of carbon dioxide or somehow reduce the heating, that they wouldn't just wind back again. Whereas if there was a tipping point, you'd reach a point where the clouds completely collapsed, and you'd have to cool to a point even lower than when they collapsed for them to come back again. So I think it's a feedback rather than a tipping element. But that's maybe being a little bit pedantic. But I do think we need to be careful about defining things as tipping elements or tipping points. It's a little bit like Arctic sea ice. It's a feedback. It's not a tipping point. If we were able to cool the Arctic, then the sea ice would come back again. It wouldn't reach a point where it collapsed and we have to cool it all the way back down to pre-industrial for it to suddenly reappear.
Mm-hmm. Great. Well, we got 3 minutes left. Greg, do you have a quick question? A very quick one.
Okay. I was going to ask Jan about tail effects or tail risks, but this is part of there's the nomenclature is a bit confusing. Tail risks, feedbacks, tipping points. But let me just ask about in all of your movies, you show the temperature distributions all over the oceans, but the land masses are all grayed out. Now, I would think that seeing the movie with the land masses maybe in some different color scheme, but just to show how they're varying would be an important addition to your presentation. What about that?
I mean, I would like it. Maybe also, you would see that land temperatures also increase fast, but what we see is that marine heat waves and surface temperatures really regulate a lot of stuff like poleward heat transport with sea surface temperature pattern, and would make sense. But I think the ocean perspective was overlooked so long, though good to really focus on it. But
yes, I understand why you chose that, but I mean, ultimately, it is this global system which has land masses affecting ocean and ocean affecting land masses, and that would be good too. I would like to see the depiction of that. But anyway, some more work for you.
Okay. Well, I think it's time that we wind up now. We've gone for an hour and a half, and this has been a really eye-opening session.
Dennis, this is just a really, really quick comment. Because I did respond in Tom's Substack about the possibility of ocean thermal energy conversion. And it's an interesting one because it doesn't provide a whole lot of cooling, hence we didn't really focus on it as a cooling of the atmosphere. It doesn't provide perhaps a whole lot of GHE, be replacement, basically replacing fossil energy with ocean gradient heat energy. But it does actually, significantly, it increases the circulation, the ocean circulation. I mean, you're pushing the heat downward in Jim Baird's version of that, him and some other folks. So it's just something to consider. I mean, maybe in addition to studying this more, we need to focus more on methods that do actually directly address ocean stratification and its and heat in general, and try and do something about that. So just a comment.
That's a very interesting point, Ron. I think this topic of marine heat waves has so many dimensions and is so alarming and new on the scientific scene. We're going to have to put more emphasis on taking it apart as we go forward. So let me, on behalf of our colleagues, thank Tom and Jan for this really interesting and alarming description of a phenomenon that's going to have to really come into our discussions to a much greater degree. Thank you both for joining us, and we hope that you will continue publishing on this, because we need to get the broader scientific community engaged on this issue, most definitely. Well, thank you all, and see you in a couple of weeks.